Mesdames et messieurs, ladies and gentlemen, veuillez accueillir, please welcome Yoshua Bengio.
Hello. It's my great pleasure today to tell you about some of the work we're doing in AI and machine learning research that's connected to the big problem of climate change. And in particular, I'll tell you about a project to visualize some of the changes that are likely to come to us, in fact, that are already happening in some places. So I hope I don't need to convince you that something really big is happening to the planet. That's the fault of what we've been doing, producing greenhouse gases. And it's something that's a little bit difficult for many people to grasp because it's not something we might necessarily experience ourselves, but our children and grandchildren will most likely pay most of the price for all these gases we're putting in the atmosphere. So here in Quebec and in other places in Canada, recently we've been suffering from flooding. And this is a picture of a flooding that happened just 2 years ago. At that time, people said, this is a very rare event. Our insurance and our statistics tell us this is a once in a 1,000 years event. That was 2 years ago, and just this year we had about the same thing. So lots of people around the world from many communities, but in particular in the scientific community, are rising to that challenge and are thinking, what can we do? Maybe one of the greatest questions that remains partially unanswered is, and it has to do with the willingness of people to actually act and to invest to reduce the issue of climate change, as that they're afraid of the negative impact on the economy of actually doing things like a carbon tax. But even though those calculations I think are very conservative, economists already are being able to predict that if you put in the cost of mitigation and adaptation in the balance and the savings, if we act early, just in dollar amounts, not even speaking about the human costs, the advantage is already clear in terms of acting very, very fast. And so there's a table here that shows the number of billions of dollars per year in GDP in different countries, and over the year, over the planet, we're talking about trillions of dollars. So I want to mention that it's not just bad things. We can act, and there's a group of people who have proposed a list of 100 ways that we can act to reduce climate change effects with what's called the Project Drawdown, so I encourage you to have a look at that. But in my community of machine learning researchers, we are asking ourselves, what can our expertise do to help deal with this issue? And there are many ways that actually we can do something. We're preparing a paper that will come out in just a few days on precisely how machine learning can help dealing with climate change. So I'm going to go through some of the ways that this can be done. On the side of the energy consumption and the ways that we could optimize and reduce our energy consumption, there's a lot of possibilities. And machine learning can be used to predict various things based on what we're measuring now. That can be used to optimize all kinds of decisions about how energy is consumed, how it's priced, how it's transported. And this is particularly important for renewable energies. So what I mean is that there are what's called variable sources of energy, like solar and wind, where it's very difficult to predict ahead of time how much power will be available, because if it's sunny, you get more power. If it's not windy, you get less power. And in order to be able to compensate for these variations, we need to be able to predict those changes as efficiently as possible. So that's one place where we can use machine learning to help these short-term predictions that are going to allow us to optimize how the energy is going to be managed in the grids in various countries. And that's on the side of producing the energy, but also we can use machine learning to help predict demand. So of course we can use seasonal statistics, but we can do better than that. More and more there are sensors in many, many places in cities that allow us to do a better job of predicting how demand is going to be changing in the next few hours or the next few days. That can be used to change the prices, to reduce consumptions, or to change the patterns in which energy is distributed. Other very important areas where these kinds of machine learning predictions can be used include transportation, construction, and industry. So in terms of transportation, by again improving what the demand on the transportation network will be, in the longer term, we can improve urban infrastructure. In the shorter term, we can improve things like traffic signals and the flow of traffic. Similarly, we can use these things, these predictive methods in construction and industry, for example, to optimize supply chains or to optimize transportation routes. So for example, there's a project at Element AI, which is in partnership with the Port of Montreal, which combines AI and operations research. So what does that mean? We have different vehicles that are transporting goods, and they sometimes waste a lot of time because of poor planning. If we can do a better job of predicting what will be needed to be transported from point A to point B for all many pairs of points, and what the traffic and the conditions will be, then we can do the OR part, which is optimize, right? So the AI part is about predicting the probability distribution of various events, and the OR part is, well, given that pattern of possible futures, how do we take a set of coordinated decisions that optimize some objective, for example, to reduce the amount of energy that is being used in transportation. There are many projects that I could talk about, but one that I'm involved in more closely, and that's very different from what I've been talking about, and very interesting in what it reveals about the recent progress in machine learning, has to do with synthesizing new materials. New materials could be useful to build better batteries, for example, which is a big bottleneck today for things like electric vehicles. And so how does machine learning come into this design question? Well, there's been progress in machine learning that I'll actually come back to later that allow these deep networks not just to classify and predict, but also to synthesize, to imagine new things like images, but also molecules. In fact, we also have projects in a similar spirit to synthesize new molecules for drugs. For materials, it's actually more complicated than drugs because it's not like a single molecule in isolation, but it's a lattice of molecules, as you can see in the picture, where the same pattern, if you want, group of atoms, is repeated many times in 3D. And so first, we're using these models to predict the properties of the lattice, the material that we are thinking we could potentially build. If the material that we are evaluating virtually in this way looks good according to those properties that we're predicting, then we might go to the next stage in order to actually build those materials and evaluate them for real. So it's sort of a virtual screening for materials. There's another area where machine learning is really interesting and people are starting to explore how to use them, is to improve climate models. So these are long-term predictions, and up to now these models are physical models that have very few degrees of freedom, that make fairly strong approximations about the physics or the chemistry of the weather and the climate. unfortunately, these models are, well, on one hand, imperfect because of all these approximations, and on the other hand, they're very, very slow in terms of computation. They require huge amounts of computations. So what people are doing with machine learning these days is trying to train these statistical models to either just imitate those physical models but do the computation faster, or actually potentially improve of them by using additional data. So as I said, those physical models only use a few free parameters that you typically find in those physics-based systems, and so they can't be fit very well to the data. But if we use instead these statistical models, and they both try to agree with the physics, which is approximate, and the data, which is insufficient. We are combining two kinds of constraints that allow us to build potentially much better predictions. Let me tell you about the figure here. So what it shows is the temperature change from now to the future after the vertical line, according to different models and different scenarios. And one thing that people should really understand is that there's a lot of uncertainty about those models, that under not just different scenarios, but also different assumptions that one can make, actually the change in temperature could be much worse than what you read, for example, in the IPCC report. And the reason it tends to be that way is that those reports, they want to be conservative. They don't want to exaggerate what will happen. But in reality, there's a sort of worst case scenario are much worse than what you're hearing about. And that uncertainty is very difficult to understand and manage. But it's something to keep in mind as we're thinking of the economic costs of not acting fast enough. So now I'm going to tell you about, I think, one of the bottlenecks for our lack of doing the right things as a society with respect to climate change. Why is it that our governments are not acting as quickly as they should? So, scientists say you should act, and rationally, you expect that governments would do it, but it's not happening. And there are a number of reasons. So I mentioned already the economic fears that the cost of mitigation is going to be something we have to pay up front. So that for sure is part of the equation. There's also a game theoretical issue that we don't have the sufficiently strong international governance to take those kinds of decisions. So what happens is it's the individual countries or even states or provinces like here in Canada which are left to take those decisions, which means paying a price in the short term for a benefit in the long term. And that benefit is going to be shared across the whole planet. And so there's a prisoner's dilemma issue, meaning that as far as the individual interest of each country is concerned, it may look like, oh, why would I spend money on this when the others might do it, right? And why would I do it if some other big countries are not doing it, right? So we're kind of stuck waiting for each other to actually act. However, acting later is going to cost us a lot more. So we're like all losing. So why is it that we're not understanding this game situation in which we're all losing? Well, we need decision makers to understand that, and we also need to address the psychological biases that have to do with human nature. So it's actually difficult for us to really fathom these events that are going to happen far in the future or far away from where we are. And of course, there's the effect of a number of companies that stand to lose when we change the way things are done in our society, and these companies might be very powerful. So we need to make sure that democracy plays its role here. But let me go back to the issue of psychological factors. Psychologists have demonstrated for a long time, in fact, some of the Nobel Prizes in psychology, in economics actually, because there's no Nobel Prize in psychology, were given for the study of human biases, cognitive biases, so that we're not always rational. I'm sure you're not surprised by hearing this. And it's particularly hard for us to be rational about something for which we don't have an immediate emotional connection. And something that is out of sight, out of mind, and far from our emotions is difficult to really handle properly when the short-term fear about, say, losing one's job if you're working in an industry that stands to lose, for example, is very strongly impacting us emotionally. So, so what can we do to counter these biases that are making us, or at least a majority of people, underestimate the stakes of climate change? So I'm going to come back to that, but for now let me tell you a little bit about those climate models relating to flooding, which is something we've been studying. So flooding is actually harder to predict than other aspects of the climate. It's fairly easy to predict the rise in the sea levels, although there are issues there as well, because the current models are assuming that for so much increase in greenhouse gases, we get so much increase in temperature, and then that can be translated in the amount of water in the oceans. Unfortunately, there are non-linear effects that are kicking in that are, for example, when the ice is melting in the North or the South Pole, this is actually not just producing more water, but also allowing more heat to be captured on the Earth, because those white ice sheets were sending heat back in the atmosphere, and it's not going to happen anymore. So that's one aspect. Another aspect on the side of flooding, here in Quebec, we had a lot of flooding. Of course, that had nothing to do with the sea level rise, but had to do with rivers and lakes, and the spring flooding due to the snow melting and spring rains. So these are harder to predict, because predicting the patterns of rains, for example, is actually something fairly difficult. But there are models, and it's interesting to see what they're telling us. What we find is that not only there is a pattern of worse effects as you go higher up north in terms of temperature, but also in terms of precipitation. So there'll be a lot more rain coming from the northern parts of the country, for example. All right. So now let me tell you about a project that tries to do something about those psychological biases that I've talked about. So we'd like to communicate with people what's going to happen with climate change and how our decisions now can have an impact on the future, but showing them, you know, the scientific jargon and you know, hard to read statistics and probabilities is not very effective. So what we're exploring is building a kind of educational tool that will allow ordinary people to not just look at those statistics, but also visualize in a personalized way how climate might impact them. And of course, climate might impact them in many ways. And right now, we're just focusing on one thing we think we can do fairly well, which has to do with flooding. But of course, there are many other climate effects, such as fires and other extreme events, weather events, and maybe even more importantly, the global economic impacts due to hundreds of millions of people being displaced. So the idea is that in order to make people visualize the effect of these climate events, we're trying to show them things that are close to them emotionally, like their house. How is going to be their house in 50 or 100 years if we continue with the current route, or if we increase the, say, the price of carbon? Of course, that's for places which might be close to a river or the sea. So we don't want to just induce fear, because it's been shown in studies that the negative emotions are not really efficient at getting people to act, especially to act in a less selfish way. Because actually, you know, it's a global thing that is happening. The damage is not going to be just local, it's going to be across the planet. So yes, we want to show something personalized, like your house or your friend's house, but we want to put people in as positive a mood as possible. And for that, we want to allow them to see what would happen if we act positively in the next few years. The other thing is that we're very wary about the potential for viewing this kind of project as some sort of propaganda. And so we want to make sure that the predictions that will be made are going to be grounded on the best current climate models and the best science about where, for example, flooding is going to happen, with what probability, at what level, and things like that. Now, let me tell you a little bit, in the time that is left, about the kind of machine learning techniques that we're exploiting to build this application. So the GANs, for Generative Adversarial Networks, is something we invented in my group in 2014, and in the last few years, they've been amazingly successful in the research in machine learning. And what they allow to do is, as I mentioned earlier, to reverse a little bit the neural net. Instead of going from, say, images to categories, we can go from categories to images, right? So what it means is that there is missing information that the model will invent, just like an artist. So it's being creative. As you can see by the label, the image on the left is a real image, whereas the image on the right is an imagined face. Like, this person does not exist. And it's very hard to see the difference. Actually, there are people who are building systems that can tell the difference, which is another story that's interesting. So this is the kind of technology that we would like to exploit. Right now, it can be used to synthesize objects of a particular category, like faces. Here is the case where it works the best. But what we're trying to do here is different. We're trying to transform an image, like your house as it is today, into how it might look if it was flooded with a particular level of water, for example. So there's a traditional way of doing this in machine learning, where we have inputs and target outputs, and some neural net is trained to go from inputs to outputs that are supposedly close to the target. So for example, if we had images of horses and the corresponding image of a zebra, we could train a neural net to go from an image of a horse to the image of a zebra. But of course, such pairs don't exist in reality. And so we have to do what's called unsupervised learning of these transformations. To give you an example of what it means, it would be like trying to learn to translate from French to English, but not having pairs of sentences, one in French, one in English, which would be the corresponding translation. Instead, just having a lot of French sentences and a lot of English sentences, and hoping that we can find a sort of nice transformation, nice simple transformation that maps French sentences to English sentences. Now, there's a kind of GAN that is able to do that. It's not perfect, and you can combine these unpaired examples with paired examples to improve the quality. So here, for example, you can see that this kind of system actually learned to map from images of horses to images of zebras with no paired images, because the only thing the people had who did this are a bunch of images of horses and a bunch of images of zebras, right? So people are starting, researchers are starting to use these things to actually carry an emotional message. So this is an example of a project that is happening at MIT, where they took images from cities here in North America and transformed them so that they would look like cities that have been destroyed by war in Syria. So it's kind of an attempt to provoke empathy by transforming something you know into something that would make you feel safe for the people who are suffering from war. So we've been starting to apply these kinds of techniques to map images of houses in a normal state into images of houses that have been flooded. So what you see in the figures are these pairs of images, where on the left of each pair you have the original image, and on the right you have an image that has been created by these GANs, but with a sort of a flooding state. And right now the systems can work in some cases, but still doesn't work well enough. The main bottleneck for us right now is we don't have enough images of flooded houses. So we're going to put out actually an app that anybody can upload images of flooded buildings or flooded roads or flooded houses and so on to help us collect more training data for this project. So to close, I want to mention that this project is actually highly multidisciplinary. So we come in my group with the expertise in machine learning and GANs and so on. But in addition to the AI expertise for this kind of project, you really need people from many other disciplines. So of course, we need people with the climate science to build the underlying predictions about the future in different places. We're also working with people with expertise in behavioral science to better understand these emotional aspects and these cognitive biases. We're also starting to work with economists, because I think one of the biggest questions for understanding what kind of future lies ahead of us and how our actions today will impact that future is what's going to be the economic impact of the disturbances created by climate change. And economists are starting to do that, but there's still a lot of work to do. And of course, we're also working with web development experts and user interface experts to build the kind of apps that we would like people to feel good about and to have an impact on their thinking and their behavior. This work is in collaboration with a number of partners, in particular Microsoft Research, Element AI, and another research organization, CREG, here in Montreal. So that's it. Thank you very much.